Hello, good afternoon. I'm Charles Bouman. This is E637. And let's see, we're going to pick up on the material that we were just talking about MRI scanning and how it works from both a very simplistic physics point of view, but more to the point of this lecture from a signal processing point of view. So let's see. So the basic concept in MRI is that you put a nuclear species that has a magnetic dipole in it in the presence of a magnetic field, and then it precesses around the axis of that magnetic field, much like a top would precess that was spinning. And it turns out that the frequency of precession around that axis is proportional to a fixed constant times the magnetic field strength for any particular nucleus. So here, if this is hydrogen, if you recall, has one proton, right? It's the simplest element because it has one proton, and if it's not an isotope, then it has, I think, no neutrons. Correct? Is that correct? Yeah, I think that's correct. But okay, so it's just a single proton. So actually, if you have hydrogen, if you have ionized hydrogen is just basically protons. It's pure protons. So anyway, so hydrogen, if it non-radioactive hydrogen or what do you call what's the opposite of being an isotope? Well, the normal version of hydrogen with one proton. If it bonds to oxygen, it forms water, and water is in a lot of tissue, biological tissue. So basically, humans are primarily composed of water in soft tissue. So the hydrogen, and when you have a chemical reaction like that, it doesn't really change the nuclear properties. There are some very, very specialized cases in which there's interactions between nuclear and chemical properties, but for the most part, they're independent because nuclear properties have something to do with the underlying structure of the nucleus, and chemical properties have to do with the interactions of electrons, right? I mean, so for the most part. So you can bond it to other things and make other materials out of it, but in the end, you're really looking at the protons. And the protons then are in this magnetic field, and there's a constant. So it turns out, I think the constant, somebody looked it up on Google, so I assume this is approximately correct, that at 1.5 T, it's 63 megahertz. So I guess it would be, at 3 Tesla, it's 126. So it's roughly 126 divided by 3 megahertz per Tesla, right? But 1.5 T and 3 T are two sort of pretty standard magnetic field strengths for MRIs. So basically, if you have a 1.5 T MRI, the protons will oscillate at approximately 63 megahertz. So what ends up happening is that you can use an RF signal, you transmit an RF signal at 63 megahertz into the material, and that RF signal will cause these atoms to precess. You'll basically pump energy into it, and they'll precess, okay? And the way they describe that is the tip angle increases. I mean, this gets into more physics than I want to deal with here. But and then if you remove the excitation in the form of the RF signal, they'll actually re-radiate energy out. So they'll transmit at that same center frequency. Okay? So that's the underlying phenomena we're going to use to do this. Now, what ends up happening is actually quite interesting that MR scanners, traditional MR scanners, use very high field strengths. They're kind of state-of-the-art, sort of not clinically used, but there's talk about low field strength MRIs that would use superconducting detectors, but that's not really practical. What's used clinically is high field strength. So, and you need the high field strength in order to get the signal to be strong enough that you can detect it reliably and form a high quality image. So to do that, you have to form, something on the order of a 1 Tesla field, or 1.5 is pretty standard these days. Clinical MR scanners go up to 3 Tesla. Beyond that, it's a research scanner, because I think FDA approvals for anything below 4 Tesla, but manufacturers don't make, I don't believe, at least not ones I'm aware of, make 4 Tesla scanners. They make 3 Tesla scanners. So that's sort of the highest level of clinical scanner. If you get like a 7 Tesla scanner or a 5 Tesla scanner, you can't use it clinically, because it's not approved for clinical use. I mean, I guess there's some questions about what at those field strengths, what the effects on they haven't done the studies, basically, I guess, to verify that that's okay, so that they're not yet fielded clinically. But they are used for research applications. So that's a very high field strength, 3 Tesla or 1.5 Tesla. So to achieve that kind of field strength in any kind of practical sense, and also it has to be, you want a relatively large bore so that you can get people in here, and actually people seem to be getting larger with time. So that getting a large enough bore here is a significant issue. So what you do is you have a superconducting magnet, which is really quite fascinating. So when I'm not an expert on superconducting materials, but basically these are certain metals become superconducting below some particular temperature. So it's usually, I think it's on the order of a small, say a few degrees Kelvin, where 0 degrees Kelvin is absolute zero, right? So this is quite cold. And at a few degrees Kelvin, below a few degrees Kelvin, the resistance of the wire to current becomes 0. It's not small, it's 0. So it's quite fascinating. You take this current, you take the magnet, it has to be in a bath of liquid helium, because liquid helium is cold enough. If you recall, helium is a noble gas, so it only forms a liquid due to, I think it's called the Van der Waals forces, at very low temperatures. So you basically take a generator and you put current into this thing, and then you disconnect the generator. Now, I'm not exactly sure I understand all the details of that. I haven't actually seen it occur, but that's what they do. And what happens is once the current's flowing around there, it just keeps going and going forever, like a perpetual motion machine, because there's no resistance. So the current just keeps flowing. So one way of thinking about it, you say, well, gee, that's really weird, okay? I mean, it's like, you're telling me a car with no friction on the surface of a road. Well, yeah, but the one way of thinking about it is as if you have, imagine you have a magnet, like a refrigerator magnet, right? It's in a permanent state of magnetization, and that's sort of what this is. It's like a permanent magnet. The magnetic field doesn't decay with time. The current just flows around there, and you can come back, a few years later, and it's still the same. Now, what does change is that the liquid helium will boil off with time, so you have to kind of constantly replenish it, because there aren't too many spots around town that are around a few degrees Kelvin, thank goodness, okay, even this time of year. So this will warm up with time as the heat penetrates the jacket. I mean, you have insulation and so forth. And actually, there's a phenomena, and all MRs, this doesn't happen too often because the magnets are designed to be pretty robust. But every magnet has to be designed to handle the event of what's called quenching, which is that if enough of the helium boils off, that some of the magnet becomes exposed. Like, for instance, if there was a power failure for a long time, right? Eventually, if you have no electricity, then there's no electricity to replenish. I mean, they actually have a cooling system that replenishes the liquid helium. But eventually, the liquid helium will boil off, and some of the magnet would become exposed. And when it becomes exposed, the magnet actually becomes resistant to. It might be just a small resistance. And if you have an enormous amount of current going through a very small resistance, of course, that produces heat. Well, the heat now will then boil off more of the helium, and you have an exponential growth of boiled off helium and heat, right? So what effectively happens is that basically all the liquid helium boils off in a very short period of time. You know, you could call it sort of an explosion, right? Because you have an exponential growth. And it blows all the helium out. So the heliums, the magnets have to be designed so that they can vent that helium if the magnet quenches. And then, of course, the other problem is that there could be a person there, okay? So it has to be designed so it vents the helium out through the roof. And that if you're in the room, it's always best if the doors open outward. So if you're ever in an MRI center when the magnet quenches, which I don't think will happen, but just in case, then remember that the first thing to do is to get out of the room, because you can't really breathe helium very long because you don't get any oxygen, okay? And you know, so it is actually a serious safety concern. They have to have oxygen nearby, and it's best if the doors open outward, because otherwise the doors can become pressurized in a closed state. So I think that's kind of fascinating myself. But anyway, so the upshot is you got a magnet, and it's a really, really strong magnet. Okay. Oh, also, don't walk into an MRI center with a belt buckle that's made out of ferrous material like iron, has iron in it, because there's an incredibly powerful field, right? It'll shoot that sucker out of there like a bullet, okay? So that could be, it's not too good, okay? So there's safety concerns there too. Okay, anyway, it's fascinating stuff. Okay, so anyway, so I'm getting back to the mathematics. Now we're going to treat the magnetic field as a scalar, even though it's really a vector, because we're going to assume that the direction of the magnetic field is constant. It's just the magnitude that's changing. Okay, so the magnitude m of xy, so it's in 3 dimensions. The magnitude m of xy. Oops, gosh, I noticed this mistake before, and I keep forgetting to correct it. Okay, I'm going to have to make sure I do that. Okay, so it's really m, x, y, and z. There's supposed to be a z in here. Okay, so m, x, y, and z. So so the magnetic field strength is going to vary as a function of position. Now the reason is you actually designed the magnet so that the magnetic field is as uniform as possible in the area where you're going to do the imaging. But then they add what are called gradient coils. So the gradient coils are coils that introduce a variable magnetic field. And you control those through amplifiers. So they're like coils you might think in a speaker, right? So a coil, you should know from high school physics, right? That if you take a coil like this of wire, and you have current going in like that, right? That let me see. So, well, I guess it depends on how you view that. Okay, but let's say if the current is going this way, then the magnetic field goes that way. It's the right-hand rule. Okay. So as you increase the current, the magnetic field strength, magnetic field strength is proportional to the current, and there's some concept of proportionality, which is usually like the letter M or something. So the magnetic field is L or something times I, right? Well, we'll call it L. I think I probably used a different letter later on. But there's some concept of proportionality. So the more current goes into this thing, okay, the stronger the magnetic field. And then this is designed so it's not a uniform magnetic field. It's a magnetic field gradient, okay? And there's tricks to do that. So what will end up happening is that the magnetic field changes approximately linearly with position, okay? One thing to remember also is that if this is an inductor, then if you recall, the derivative of the current with time is equal to the voltage times the of time times the inductance, right? Hold on. No, divided by the inductance, right? So the other way of putting it is like this. the IDT times L is V of T. So anybody who's ever unplugged a vacuum cleaner knows about this, right? Because the vacuum cleaner is highly inductive. So if you have, this is the wall socket, right, and that's the wire, and then the vacuum cleaner is running, and you pull the socket out, what happens? Oh, you must have noticed. So you have a vacuum cleaner here, right? Right. Well, it turns off. Yeah, that's one thing that happens. That's the vacuum cleaner bag. So you get a spark. Everybody knows that, right? Haven't you ever noticed that? You obviously don't vacuum your room very often. Oh, okay. Oh, you're okay. I'm too lazy. Okay, I always, sometimes I'm lazy. I'm like, I pull the cord, you know, and it unplugs, and you see the spark, right? You've seen that. You must have seen that before, right? So why is that? Well, because the IDT is infinite there, right? The change in current is infinite, but this is highly inductive, so the voltage is enormous. So you get a spark, right? So the consequence of this is that the magnetic field here is actually going to be not the integral of the voltage, but it's going to be proportional to the second integral of the voltage. D tau. It's the second integral of the voltage. So the first integral is the current. Hold on. No. Wait, what am I saying? The magnetic. Oh, I'm sorry. I got it wrong. The magnetic field is the first integral of the voltage. It's going to be the second integral of the voltage in a little bit because we're not going to be looking at the magnetic field. So I'm just letting you know that you have an amplifier here, plus minus, and the amplifier drives this thing with a voltage, V of T, and the current is going to be the integral of the voltage. And the magnetic field is going to be proportional to the current, right? So that's how it works. And this will produce a linear magnetic field gradient, okay? This is distinct from the uniform field caused by the superconducting magnet. The superconducting magnet produces a static, hopefully uniform magnetic field, and to that you have an additive constant of a gradient magnetic field which varies linearly with space, okay? And it's produced by the actual current through a coil that's driven by an amplifier. This magnetic field is very weak compared to this magnetic field. And this magnetic field has to be done with a superconducting magnet because it's so strong. But this magnetic field can be just done with a regular amplifier through a coil. And the coil is designed so that it's a linear gradient in the magnetic field. Now, there's actually not just one coil, there's three coils. There's one coil in X, one coil in Y, and one coil in Z. And each of those coils controls the magnetic field gradient along the three axes, okay? So by varying the current through each of those three coils, I can vary the gradient of the magnetic field in each of the three directions, okay? So here is a figure that sort of illustrates this as best I could. Okay, so we're just considering Z. Z is normally the axis along the bore, and the patient is normally positioned inside the bore this way, right? So it might be actually their head, or it could be their body, or it could be a leg, okay, depending upon what you're imaging. So if the magnetic field gradients are set to 0, then the gradient is 0. But in this case, the gradient's not 0. We're seeing that the magnetic field shifts slightly as you go in the z-axis. So the gradient here is set to be, so G of Z is the gradient. G of Z is set to be a positive value. So as you move in the Z direction, the magnetic field increases, okay? Now what you do, so you set this to some positive value, and now you put an RF pulse with an antenna, and you transmit the RF pulse into the patient. You know, RF just passes through tissue, radio frequency, because it's like radio waves, right? It's not absorbed. There's some absorption by water, but not a lot. Okay, that's why. By the way, I mean you can transmit radars, weather radars work, right? In fact, you have to design them so that they're a little sensitive to moisture, so you can see the weather. But the reason radars work, even though planes are flying in fog, is because at radio frequencies, electromagnetic energy penetrates the moisture in the air. So the RF frequency at 63 megahertz will go through your body, and what will happen is it will stimulate the precession of the protons, but only for those where the resonant frequency matches the RF frequency. So if this is at 63 megahertz, let's say if it's 1.5T, let's say it's 63 megahertz, okay? Now, if you're right at the center of the gradient, then the magnetic field is exactly 1.5 Tesla, and at that point you get a resonance, okay? But if you're off center, then the magnetic field is either larger or smaller, and the resonant frequency shifted a little bit up or down. And because it's shifted up or down, then the RF signal at 63 megahertz is not tuned correctly. So the protons won't resonate. So the only protons that resonate are the ones that are right at the resonant frequency, which in this case is 0. Does everybody understand that? Now, you could actually shift the center frequency of this a little up or a little bit down, and then you could basically stimulate the precession of atoms in a different slice. But notice that all the atoms that are at the same resonant frequency represent a single two-dimensional slice, all constant Z. So this is called slice select, because you're selecting a slice. You're stimulating the precession of the atoms just in that one slice. Now, if you think about it, what's really happening here is at each position, the atoms are tuned to a different frequency. So if you took this signal in time and you take its Fourier transform, that's the shape of the response you're going to get here. Okay? So if this is a sinc function in time, if it's a modulated sinc function, if you take a sinc function and you modulate it onto a carrier at 63 megahertz, then you're going to get a slice here, which is a rectangular slice. And the width of the rectangle depends upon the sinc you used. If you use a very, very long sinc, then in frequency, if you have a sinc function, so this is time, and this is frequency. Okay, so if you have in time, if you have a sinc function which is like this, okay, in frequency it looks like this, right? And if you stretch it out in time, what happens to it in frequency? It gets narrower, right? And if you make it narrower in time, it gets wider. So if you have a long pulse, a long sinc, then you get a thin slice. If you have a narrow sinc, you get a wide slice. And of course, you want to pick those slices so that they fit together. What you really want to do is you're going to do a sequence of slices to do a 3D reconstruction. So you're going to fit those slices together next to each other. So okay, so that's slice select. The sinc function determines the width of the sinc, determines the width of the slice, where a wider sinc produces a narrower slice, and the center frequency determines the position of the slice, because it's not just a sinc; it's a modulated sinc, right? If you take sinc of t over t, and then you take it times cosine of omega 0 t. So this is the modulation, and that's the sinc. So if you modulate it up to a frequency of 63 megahertz, then when you take the Fourier transform, you'll actually get the Fourier transform of this will look like this. You'll get a pulse here, and you'll get a pulse here, like that. Oops, yeah. You'll get a pulse here and here. So the center frequency here will be omega 0. This will be minus omega 0. And then the sinc will determine what each of these little pulses look like, right? So if this isn't familiar with you, go back and, I know some people haven't had as much background in linear systems, okay? Okay. So you need to review that if that's not familiar, okay? So, right. Now the question is, now what happens is that, so what is that? That's a person. That's what people look like. Earthlings, as a matter of fact. But you have to slice them through the middle, okay? So if you slice a person, they kind of look like that, right? Because those are the two lungs, and that's the backbone, and that's their arms, okay? Okay. So actually, if you look at enough of these, it becomes natural. It's a little freaky, but... Okay, anyway, so this is what it looks like. So now after you've transmitted our pulse and this thing is oscillating, now they'll re-radiate. And so you pick up an RF signal. And so now the question is, how do you form an image from this 2D slice? Because otherwise you're just going to receive the entire signal over all this. So you're going to measure the total volume, but it doesn't give you much information, right? So you need to be able to form an image. So how are you going to do that? Okay. Okay, so that's where the tricky mathematics come in. So let's first look at what the signal is we receive from one voxel, and then we'll ask what happens, what's the signal, then we can determine the signal we get by adding all the voxels together. So we'll consider one voxel of size, dx, dy, dz, and then we'll integrate them all together to get the total signal that we receive, okay? So the received signal is going to be from the voxel at, this really should be r, x, y, and z. Oh, well, we can remove z because we've assumed that we selected a slice, so it's all the same z, okay? Now, there's going to be some function f, x, y. I guess we could have said this was fxy of z, because it's for the particular z. I could have put a z0 in there or whatever. But then, so the signal we receive will be that times some phase. Now, this is complex notation. If you take the real part of that, that's what you would actually receive physically in the antenna, but this is standard notation when you have a modulated signal, right? So this is some voxel-dependent weighting, and then this is the phase, due to the fact that you've changed the linear gradients at this point, potentially, okay? So the phase can be modulated by g of x and g of y. Now, why is that? Well, first of all, the phase will change with time because if you have a signal, let's say e to the j omega t, right? That's a frequency that's a signal with constant amplitude and fixed frequency, right? So that's equal to e to the j phi of t. So where phi of t is equal to omega t. So if you have a constant frequency signal, the phase increases linearly with time, right? Now, the other way of looking at it is you'd say, well, if you have a signal with e to the j phi of t, what's the instantaneous frequency? Well, the way you normally think of that is that the frequency f of t is equal to d phi of t dt. So the time derivative of the phase is the instantaneous frequency. And then by that logic, the phi of t is equal to the integral from, say, 0 or minus infinity to t, or whatever you want. It's an indefinite integral of f of t, f of tau, d tau. So this relationship, I always remember, was a little counterintuitive for me, so I have to always rethink it out. That the instantaneous frequency is the derivative of the phase, and the phase is the integral of the frequency. All right? So okay, fine. Now, we can change the frequency by changing the gradient in x and y. Because if we go back and look at this thing, each voxel is the frequency of oscillation is going to be modulated by the intensity of the magnetic field. Because the magnetic field times the gyromagnetic constant determines the frequency, right? So if I increase the magnetic field, the frequency will increase. If I decrease the magnetic field, the frequency will decrease. So I can change the instantaneous frequency by changing the gradient. Now, I won't mess around with the gradient in Z, but I am going to change the gradient in X and Y. By changing the gradient in X and Y, I can change the oscillation frequency of that voxel. Does that make sense? Is that clear? Because going back to the original basic result, this is the basic result. The oscillation frequency is the magnetic field times this constant L. So L is not changing, but if I change the magnetic field, the frequency of oscillation will change. And one way to change the magnetic field is to change the gradient. Now, if the voxel is right at 0, 0, changing the gradient won't matter. But if it's anywhere else, changing the gradient will matter. Okay. Now, we'll assume that phi of 0 without loss of generality is 0, and that just means we absorb any complex constant into f of xy. So f of xy can be a complex number. Yeah. Yeah, this one here?
Yes. Is this because of shifting frequency?
Well, no, it's just that this received signal is a modulated signal, right? I mean, nominally it's coming in at 63 megahertz. So it's not going to be just a constant that's real valued. It's going to be, I mean, the way you represent in communications, if you have a signal, say S of t, and it's equal to cosine of omega 0t, the way you represent that is typically in complex notation. You represent it as e to the j omega 0t. It's just simpler that way whenever you have modulated signals. So this e to the j phi is just taking into account the modulation. So we're going to expand that out in a minute, okay? So you're just taking into account the fact that it's modulated, and the modulation is going to have some frequency associated, and there's also going to be some phase. But without a loss of generality, we can just assume at time 0 it starts off at 0 phase. Okay. Okay, now the derivative of the phase is the frequency. Remember, I convinced you that hopefully. So, in particular, the frequency of a voxel at position x and y and time t is going to be the magnetic field at that time and location times L, where that's the gyromagnetic constant. So, now if the derivative of the phase is this, then the phase will be this integral here, right? So the phase is the integral of the frequency of the instantaneous frequency, and in particular, m here is given by the equation. Let me just put it up again to remind you. So m, the magnetic field at position x, y, and z is given by this expression. Now these g's can vary as a function of t. So this is also a function of t. So this is m of x, y of t is equal to this, okay? So I can plug this expression in for m, and I get this expression right here. Now, the different terms have different meanings. The first integral is the integral of L times m0. So these are all times dt, or d tau. So this is a constant. So the integral of the constant is just omega 0t, where omega 0 is just L times m0. Yeah?
Is it for even z, or z is not included?
We're leaving out z because our assumption was that z is fixed, okay, and the gradient in z is fixed. So I'm cheating a little bit because this m0 really isn't just m0. It also includes the term associated with what might be a small offset in the center frequency due to Z, okay? But that's already been accounted for. It's actually a good point. When you actually demodulate the signal in the hardware, you have to demodulate not with omega 0, but with a slightly offset frequency. But you knew that offset frequency because you transmitted with the same offset frequency. So, yeah, it's a detail that has to be taken into account in hardware. But anyway, good question. But this now this second integral here, there is a function of time. And that's the gradient itself in x and the gradient y. So if you take the integral of the gradient of this constant, which is the gradient in time, the integral of the x gradient and the integral of the y gradient, you get two functions of time. One is called kx and the other one's ky. So you just write this in this form. Now if you plug that back into the expression, then you get that, well, the RF signal that's measured for a particular voxel is going to be f of xy. F of xy is the underlying sort of signal strength and phase of that voxel. So it's actually f of xy is the thing you're trying to image. And now times e to the j phi of t. And if I plug in now for phi of t, I plug in this expression, now I get this form. So this is the carrier. Okay, that's the carrier. And this thing here is the like a phase modulation on the carrier. So when you demodulate the signal, what happens when you demodulate a signal is you have the signal R of t coming in, and you put it into a mixer, and you multiply this by e to the minus j omega 0 t, and that removes that term, and all that's left over is f of xy times this second term. That's what demodulation is in a radio receiver, okay? So you get now this, you strip off the carrier. So now what happens is that now we want to take the contribution from all the voxels, so we have to integrate over x and y. When we integrate over x and y, then we get this expression right here. So now this is really quite beautiful. Okay, so the complete received signal now is we take the carrier out, because the carrier is the same for every voxel. So it's a constant, independent of x and y. So it comes out of the integral. But the thing that doesn't come out of the integral is the integral over x and y of this f of xy times this expression here. Now, our assumption was that the gradients were linear in x and y. So then when we constructed the gradient coils, we had to do them specifically in a way that ensured that the gradients were linear. But given that they are, then this is the integral we get. Now, stare at that integral for a little bit. What does that integral look like?
Looks a little bit like a CSFT. Right? Yeah.
Does that look familiar?
So like a CSFT or something?
It's a continuous space Fourier transform, right?
Yeah.
But what are the variables that are playing the role of frequency? Well, remember, there's two variables for frequency. There's u.
Yeah, kx and ky.
And there's v, right?
Yeah.
So u is going to be kx of t, and v is going to be ky of t, right? So what you're doing here is, if you strip off the carrier and you measure the complex demodulated signal, this is going to be a complex number, and that complex number is the continuous space Fourier transform of the underlying 2D slice of the person. It's really actually quite amazing, isn't it? So guess what? This is really just okay. Now the only thing that's different is that in the continuous space Fourier transform, you'd have a minus sign there, right? So there's a negative. So I guess I'll put a minus sign here. This is really the continuous space Fourier transform of the object evaluated at minus kx and minus ky. Now, if if the object is, well, okay. Well, anyway, it's just true, okay? Okay. Then, and remember when I demodulate, I strip off the carrier. So what we're doing in MRI is we're literally taking your Fourier transform. So if you ever get an MRI scan, you could say, they're taking my Fourier transform, and that's what would be happening. Your Fourier transform is being taken. Okay. I hate it when people take my Fourier transform. Okay. Now, so here you have a signal, k of x. Okay. So now actually the reason why I use kx and ky is because the physicists, the physicists are kind of funny people. Like in electrical engineers always use omega, right? That's frequency, right? But I don't know why, but physicists always use the letter k. Okay? So k is wave number, and that's like our frequency. So this is like translation between different cultures. And then what happens is, the other thing is that electrical engineers always use j, right? But physicists, I don't know what's wrong with them. They use I, okay? Excuse me?
Until I came to ECE.
Oh, you always used I? Yeah. You know why electrical engineers use J? Because I is current. It's obvious, right? Okay, now. Okay, but you can tell I'm an electrical engineer because I always write e to the j omega, right? Okay, so, there's certain things you just can't change about a person. What are you going to do? Okay, so this is the received signal. So if you demodulate, this is the demodulated signal. You're measuring this, okay? And remember, well, what's kx and ky? It's this. You take the gradient, okay, and you integrate it over time. So basically, now what happens is this. And this is the part, in some sense, I like the most. Well, okay, now, as I said to you before, these are coils. So that the current in the coil is not proportional to the voltage. The current in the coil is proportional to the integral of the voltage, right? So current is like, it's as if you had a weight, okay? You have a mass, right? And it's on a frictionless surface, it's got little wheels, let's say. And then you apply a force, F, okay? The velocity is going to be, so the acceleration is the force, is F of t divided by m, the mass, right? And the velocity is actually the integral of the acceleration. So this is going to be the integral from 0 to t, and I'm going to make that a tau, d tau, right? So the velocity is the integral of the force. And the voltage is like the force, and the current is like the velocity. And the mass is like the inductance. And so now if I so now the position x of t, so now we'll start off at this is x, all right? So x of t is equal to the integral from 0 to t of the velocity over time, right? The integral of the velocity is the position, because the derivative of the position with time is the velocity, right? So the position x of t is going to be equal to the integral, is the double integral. And this would be 0 to tau, I guess, of f of s over m ds. And then this would be d tau. So it's the double integral. So the position is the double integral of the force. So if you have an object on a frictionless surface, right? So you have an air hockey table, which is approximately frictionless. and you have a puck here, right? And you press in some direction with some force. The position is the second integral of the force. So if you take it and you tap it, right, you'll have, the tap is like an impulse. You'll have an instantaneous change in velocity, and then from that point forth, it'll just drift at constant velocity, right? The other way I like to think about it is this is like driving this is like driving a car that has two axes of acceleration. Actually, there's Lego robotics things that do this. They have these interesting little wheels that allow you to do this, where the wheels. It's very cool. I should find one of them. How much time do I have left? Okay, so I can talk about something irrelevant for a little bit. Okay, so you have little wheels, okay, and the big wheel has little wheels on it that go in the perpendicular direction. So they're wheels that can roll, but they can also slide sideways with very little friction. And then they have 4 of these on the bottom, one of these little Lego robotics things, and the thing can move around like this in arbitrary directions, right? I want to buy a car that can do that. It would be really good for parking, okay? So anyway, what happens is, or you can just think of it as a one-dimensional car that travels back and forth like regular cars, okay? And you have an accelerator pedal. So this is like the accelerator pedal. The voltage is like the accelerator pedal, and you're driving, okay? So let's say you want to drive around with the accelerator. So let's say you start here, okay? And you want to go up here. Well, first of all, now this is an accelerator pedal where the accelerator pedal and the brake are integrated into a single system. So if you press down that way, you accelerate, but then it's strapped to your foot, and if you pull it this way, it applies the brake, okay? And in the middle, it's just nothing, okay? You coast. So what happens is this. When you step down, you step down real hard and accelerate, and then you stop and you coast for a while. Okay? And now what happens is you put the brake on, and you stop, okay? Now what you have to do is you have actually 2 accelerator pedals, because there's one in KX, there's one in U, and there's another one in V. And then you accelerate here, okay? And then you do the same thing, and you have to drive away around the K space. Actually, usually you don't do it that way. Actually, usually you do it this way, okay? Because people feel more comfortable. So this is X, and that's Y, right? So usually you drive around. You start here in the center of the space at 0, 0. And first you drive out here to the corner. Then you accelerate this way. You go down like this. And you scan through the space, and all the time you collect data. So at each of these points, you get the value of the Fourier transform in 2D. And when you're all done here, then you take all those values and you do an inverse 2D Fourier transform, and you get the reconstruction of the image. Okay? Now, there's an interesting thing here, is that if you want really high resolution in the image, remember, this is the Fourier transform. This is your Fourier transform, okay? So if you want a really high-resolution image, what do? Do you have to make the scans real close together, or do you have to make it bigger? If you want high spatial resolution, what do you have to do in frequency? You have to stretch, right? You just remember that. So if you want to make something small in space, you make it big in frequency, right? So you have to scan out a big area. But if you have to scan a big area, that's kind of slow, right? Now, if you make these things too far apart, what's going to happen? So what will happen is the smaller these are, making this small in frequency makes it big in space. So making it big in these steps big in frequency makes it small in space. So your field of view goes down. So you have the spacing between these. The largest spacing is determined by how big the person is. If it's a big person or object you're scanning, you need to put these close together. Remember, it's the same thing. Something big in space is small in frequency. Okay. So basically, you have to drive around the space to collect the data, and that's why MRI tends to be kind of slow. Although there's parallel acquisition modes, but you drive around, and then next time I'll just go over this. These are basically the accelerator pedal settings, okay? Because it's the second derivative, it's the second integral. of the voltage pulse that determines your position in K-space. And you can study these. All right? So thanks a lot. It's always fun. See you on Monday.